Hi guys, my name is Dan. I thought I'd make a short video about how I solved the embedded software Shabak challenge of 2018. It was challenging and also fun, and I learned quite a bit from it, so I thought I'd make a video sharing how I did it. Alright, so first thing is you go to the embedded software section, where they begin by describing the problem, which is they found a surveillance device attached to the Minister of Defense's car, and they basically want to know where it originated from. So they reverse engineered the device, and they're attaching a schematic of the device, the code running on the microcontroller, and a memory dump taken off the flash component on the device. And they know the guy who built it received this message, package received, on that specific time. And so they want us to extract the location information of that specific time from the data they've given us. And the answer should be given in latitude and longitude values. Alright, so after downloading the files and extracting them, we get these three files. Again, the schematics, the memory dump, and the code running on a microcontroller. So a good place to start would be looking at the schematics to get a basic idea of what we're dealing with. And we can see a fairly simple schematic here of a microcontroller. In the middle here, the Atmega 2560 connected to a flash device, and these two devices, which I didn't know prior to solving this challenge, but a quick look on Google tells us that one is the SAM M8Q one is a GPS component, and the lower one, the analog devices ADXL345, is an accelerometer. So that's these devices, and I already here, as you can see, looked for the data sheets of these devices, so I can understand what's happening here. Okay, so now we have a basic understanding of the structure of the device. Let's have a quick look at the code running on the device. Alright, so we have a C file here. We can see several functions, but let's go to the main loop here to get again a basic idea of what the code is doing. And we can see we have some sort of a while one loop here, so a repetitive task being done over and over again, and not going too much in depth in the functions, but just by function names you can get the idea that it's reading some sort of data from a UART port, parsing the data under some conditions, formatting the data, and then we have this function which is called save to flash, so it's saving that data to the flash. And this is again being done in a while one loop. Later we will go more in depth into the actual functions, but we get a basic idea of some repetitive task being done here in the code. And alright, if we look at the memory dump taken from the flash, it looks like this. So this initially doesn't tell us very much. You don't see any strings here immediately, so what we do see is some sort of pattern here, which might be a structure being written. And again, after having a quick look at the code, we are expecting some sort of data being written periodically. So this structure seems to have, it seems to like be of a fixed size, but not the 16 bytes size length that we are set to here, because we do seem, you can see some sort of a pattern here. So if we are changing the number of the columns, for example, to different numbers, we can see the pattern, right? The pattern coming through. All right, and if we set that number to 13 columns, we can see the structure more clearly. So this is obviously the data being written is obviously some sort of structure that is of size 13 bytes, because that is a very clear pattern here all through the flash, maybe with some stops on the way to maybe a different size here and there, but the size 13 structure seems to be a very important part of the process. Okay, so let's go back to the code to have a more in-depth look at what the while one loop is doing. Alright, so initially we have these two values, formatted length, which is zeroed, and a size, which is an output of the it's the return value of the uartRead function. Now the uartRead function it's defined here, but it's not, we don't have the code of the function. We can only assume it reads byte arrays from the uart, and also it gives us back this receive buffer, which probably holds the bytes that it just read, and the size value is just the size of the byte array that was read from the uart. And so if the size is bigger than 0, meaning if something was read from the uart, then the first action that is performed is a parsing of that data. So let's have a look at the parse function, which is interesting. Alright, so the parse function, it receives an input buffer, it receives a length, and then it will give us back this output buffer. So initially we see there are just some tests that the data is valid. Again, not very interesting, because if it doesn't meet this criteria, it will go back with parser invalid. So it's probably just a corner case. And then the data in the input buffer, and this is just this is a pointer to the start of the buffer. It is being compared to parser prefix 1. If this is the case, if it equals to the parser prefix 1, then res gets the parser type 1, and the same thing is happening with parser prefix 2. So what are these parser prefixes? These are definitions for GP, GGA, and GP RMC. At this point, the res variable is either parser type 1 or parser type 2. Again, looking at the majority of the cases, it might be parser invalid, but probably this is either an error or a case that is not interesting to the main flow. Alright, so now the input buffer is being advanced a few bytes forward past that that prefix we just compared to. And now it points to a character after the prefix. Now we are at this point here in the code. Now what's going on here is we see that the output buffer, which notice here, it is of different type. It's not the same type as the input buffer. It is a double pointer. So we are expecting an array holding pointers to unsigned integers. So what we have here in this loop, we can see that the loop looks for comma characters in a string, which is the input buffer. Once it finds them, it nulls the character, the comma character, and writes that location of one character past the what was until now the comma character to the output buffer's array. Now, why is it doing that? It is doing that because of the format of the data we are receiving, and you might have already been curious and looked it up online when we had this comparison here to the parser prefix values, because these values, the GP, GGA, and GPRMC values, correlate to NMEA messages, GPS messages, if we just look it up online. We can see that it correlates to those NMEA messages. So these are GPS NMEA messages that are, if we go to GPRMC, for example, this is the format of the message. It's a long comma separated string, and each value is separated from the next one by a comma. So what the code is doing here is going through the string and then writing down into the output buffers array the addresses of all the locations of values just past the comma character. So basically these locations. So by the end of this loop, output buffer's array should hold the locations of the values, just the values inside input buffer. Okay, so now that we understand the parse function, let's go back to main function to see, alright, to the while loop. So we realize that each of the received buffers is being parsed, and we now know that the result, the res variable, should hold a value which is equivalent to which message type we received, either GP, GGA, or GPRMC. Alright, now second, we have this condition which only happens if reset variable is equal to true. Now this will only happen once because the reset variable is initialized to true, but so it will go in here in this if statement. First time it comes through it, but it is then set to false, and never again is it set to true. So it means it will only satisfy this condition once, and never again in the life cycle of the device it will go through here again. Either case, whether it is going through this reset condition or otherwise, we see that there is this structure of sending the parsed buffers that we received through the parse function, sending that array to either format 1 or format 2 functions to receive a temp buffer from either of those functions. Now, format 1 or format 2 is equivalent to the parser type because we know that the res variable holds a value equivalent to the type message. So if this is one type of message, then the temp buffer will hold a buffer that is the formatted data according to that message type. And if it's the other type message, the buffer will be formatted in a different way in that format 1, format 2 functions. Now, this statement is probably more important in a way because it happens more frequently. We know this the first if statement is satisfied only once in the life cycle. So this else if will happen way more frequently. So this is very interesting, and we can have a look at the format 2 function. Okay, so this is the format 2 function. I don't want to go into that function into the bits and bytes of the function, but rather try to understand what it's doing, and maybe even get an idea of the output of this function, and maybe I can even use that output without going to the bits and bytes. So let's try to do that. So we can see that there is essentially the body of the function is the for loop, which according to this condition will happen twice. Now, what is happening twice here is there is some sort of calculation. Let's go in reverse in this function. So the output buffer is what we are getting from this function, and what's happening here is there is this whole process here, which we will end up with a number written to the out buffer pointer as a floating point number, and then it will be advanced. The pointer will be advanced in the size of a float, which is 4 bytes. So what happens here is essentially writing 2 floating point numbers to the out buffer. So it is just a buffer holding 2 floating point numbers, 8 bytes total. Again, 2 numbers, 2 floating point numbers. And what happens before that writing this whole process here? We can see that there are 2 values being translated from string to integer, and then another one to floating point, and then those 2 values are combined and calculated into a single floating point number, and that number will be the one written every time to the out buffer. So again, the bottom line here is that format 2 function just outputs to the out buffer 2 floating point numbers, total length of 8 bytes. So this is the format 2 function. So now let's have a look at the format 1 function. Now the format 1 function also builds a buffer that will be written to the flash, but as we know from previous view of the flow, this code segment only executes once because the reset variable is only true in the first in the first iteration of the loop. So I'm expecting some sort of format that will occur only once in the flash. Now I did see it twice, but it should only occur once in a power cycle of the device. So if you reset the device, we would see it again. Now another interesting thing about the structure that the format1 function outputs is that the first byte is not 1, because as we saw before, the majority of the structures written have a 1 as the first byte. But in this case, A would be set to true, and then the first parameter sent to the format save function is 0 and not 1. So if we have a look at the flash, we can see that structure here. It starts with a 0, not a 1. So this would be as expected because it's the first structure written to the flash. So it starts with a 0. And also, as we know from before, the format1 function formats a different NMEA message received from the GPS module because the parser type is different. So a format1 would format a parser type 1 message, and format2 would format a parser type 2 message. So let's have a look at the function. So this is the format1 function. The function takes the in buffer, which is an array of pointers pointing at floating point numbers, and interprets the two first places in the array as integers and copies those integers to the output buffer, and then returns as return value twice the size of a floating point, which is 8 bytes. Now, as we know from inspecting the parse function and also the while one loop, the format1 and format2 functions will be called according to the return value of the parse function, which is determined by the type of message received from the GPS module. The format1 function will be called for GPGGA messages, and the format2 function will be called for GPRMC messages. Now, if we look back in the guide, both messages hold the time of the GPS fix and also latitude and longitude information. But we will see that in our code, we are only using the format1, which formats GPGGA messages to extract the timestamp from GPGGA message, and the format2 function to extract only latitude and longitude information from GPRMC messages. And if we have a look at the GPGGA message, we can see the format the timestamp is stored in. So it's basically taking the digits from the timestamp and creating a string from them. So 8 minutes and 34 seconds past 5 o'clock p.m. will be 170834 as a string. So let's see if we can find that in the flash dump. So this is the first message being formatted by format1 function. Now we see the first byte. The length is 8, and we know these first 3 bytes are null bytes. So if we take these 4 bytes and interpret them as an unsigned integer, we get this integer, 125,000, which can also be interpreted as the hour 12:50, and the second 4-byte integer can be interpreted as a date, so the 28th of October 2018. And again, I was expecting that structure with 0 as a first byte to only appear once in the power cycle of the device, but I know it appears once more here. And this will actually be the timestamp that we will be using. And if we take these 4 bytes, again, we can interpret this value as a time. So 17 minutes past 4 p.m. on the 28th of October 2018. Now, why is the first byte 0 and not a 1 like we're used to? If we go back to the code, we can see that in the case of format 1, we are also setting the a integer to true. And this is the only time that the condition here, a equals true, is satisfied, and the first parameter we're sending to the format save function is 0 and not 1. Okay, so what's happening here in this third section? The save to flash function obviously receives this save buffer and writes it down to the flash. But prior to saving, it goes through the format save function, which is a very important function in the process of understanding what's going on here. So let's have a look at it. Okay, so the format save buffer receives an input buffer and a length, and then writes to the output buffer a different format of the input buffer. Now, what's going on here? So in the beginning of the output buffer, it will write this a parameter that it got as input. Now, as a second byte, it will write the length, and then it will copy the length of the input buffer to the 5th byte onward of the output buffer. This was a very important step for me in understanding the memory dump, because this number seemed very strange, as it leaves byte number 2, 3, and 4 empty, and then writes it to byte number 5 onward, which means in that written buffer we will have 3 empty bytes, or it will be either empty bytes, or maybe I would be expecting to see some sort of 3 bytes that the writing process would repeat these bytes over and over again because they are not changing here. And this was a very important process because after having another look at the memory dump, I would see that I could really find 3 null bytes that are repeating themselves in every line, basically, and a line is something I would equate to the structure being written. So this was very interesting for me. And assuming those 3 bytes are those 3 bytes that are skipped, then if this is the case, the byte before those 3 bytes is the length byte, and the byte before the length byte is this value, the a value. Now, if 8 is the length byte, and I would count these 8 bytes following the 3 null bytes as a part of that structure, as maybe the payload, the data part of that structure, then then this would be a whole structure from here to here, meaning the first byte is the A, which I'm not sure yet what it is, but again it's repeating itself here. And the second byte is the length. The following 3 bytes are the null skip bytes, and then we have the 8 bytes of data. And if this is the case, then those 8 bytes of data are divided into 4 bytes and should be interpreted as floating point variable. And so I gave that a try and just took those 4 bytes, and it can be interpreted into a number which is looks like what could be a valid latitude or longitude number. And not only this, but in following structure, then this number would be the same but with small changes, which is more or less what I would expect to see maybe from a sequentially written GPS data of a moving either person or vehicle or whatever. So this looks very interesting, and it looks like we have understood the biggest part of the data being written, because we can see the structure of a 1 and then the length and then 3 bytes, and then the data is repeating itself quite a lot. So this is the format save function was a very big step for me in understanding the memory dump from the flash. Okay, so after realizing what a format save does, I realized I really need to understand what triggers the should have variable back to true, because I know that this part of the code is the code that writes most of the data in the flash, and it only happens if should save is true. And I know, like I saw before, that should save is only being toggled back to true in here in this function, which is the interrupt handler for some sort of interrupt. And I realized I need to go slightly deeper and understand how the interrupts are configured and what the handlers do. Alright, so interrupts and interrupt handlers are usually configured in the beginning of the code, and indeed we can see here all of the configuration of the hardware and the interrupts and everything. And we don't see the content of these functions in this file, so I'll assume that they do what they say they do correctly, and that they really do configure the system clock, the UART, the SPI, the 2-wire serial interface. And I am left with those 2 functions, the configure 1 and configure 2. So let's have a look at what exactly they configure. So the configure 1 function writes to these values. Well, it obviously also sets the should save to false initially and the counter to 0, but the main body of the function is writing to these values. And if we look up in the datasheet, we would see that these are registers in the Atmel microcontroller. So what do those register names mean? We can see that we have the TCC R1A and TCC R1B, which are both zeroed, but the second one is then configured. So let's look at those names in the datasheet. Alright, so we can see that the TCC R1A is a timer counter 1 control register. So I'm expecting this to be the registers through which I am configuring the timer interrupt. So this one, the TCC R1B, is probably same type of register but for a different timer if we want to use multiple timers. And also this is the more interesting one because this is the one that is actually being configured. It is being configured and those beat values are being toggled to 1. So let's look those up to see what they mean. Alright, so we can find these values CS10, CS12, and WGM12, which we just toggled, and they do exist in the timer counter 1 control register B. Now if we click those and look in the table to see what it means, we can see that what we are doing there essentially is configuring a prescaler, and a prescaler is just a way to count in a different frequency than the system clock, and we can do that by dividing the system clock's frequency by a value that we configure through the prescaler. So what we are writing here is 101. So we are creating a prescaler of 1024. Now this is interesting because it means that we will be counting in a frequency that is divided by 1024. Now the only thing that's left now is this register here, which is initially maybe unclear by its name, OCR1A. But again, looking it up in the data sheet, we can see that it is the output compare register 1A. So I'm expecting this to be the register that we will count up to in the timer, and once the timer value is equal to the value that is set here in this register, an interrupt will be triggered. So we are counting essentially to that number, until that number. So now this is very interesting because we also know that our system clock is 16 megahertz. So with all the knowledge that we have now, we can calculate the amount of time between two timer 1 interrupts. And we can do that because we know that the system clock is 16 megahertz. So it ticks every 16 millionth of a second. But we know we also configured here the prescaler to be 1024. So the timer would tick every 1024 times the system clock. And we also know that the interrupt itself is triggered every 62,499 times. So if we multiply it by that number, we get a number that is very, very, very close to 4. What this means is we will get the timer 1 interrupt triggered every 4 seconds. So this is a number we will need to work with when looking at the interrupt handlers. Okay, so now let's move on to configure2 function. Configure2 function is shorter, and it configures these two registers, which again we will look up in the data sheet. And then find out that the first one is an external interrupt control register, and the second one, I'm not going to look it up now, but it's easy to see that it's the mask. So it's basically configuring an external interrupt and then unmasking it so we can handle it. And the configuration here, I'm not going to go into so much detail, but if you read the section about the configuring external interrupts, like it says here, it configures the external interrupts 3 to 0, and this correlates to the pin numbers that the accelerometer is connected to, because if we have a look at those pin numbers, 43 to 45, then again we can see those same names that we saw in the external interrupt control register. Int 0, int 1, int 2, and int 3. So we are configuring here some sort of interrupt that we are supposed to be receiving from the accelerometer. So now let's have a look at the interrupt handlers. We have the first interrupt handler here, the timer interrupt handler. Now we know that this function, this interrupt handler, we now know that is being triggered every 4 seconds. So let's see what happens in our system every 4 seconds. Fairly simple logic. We have this counter that is advanced. We know this counter was set to 0 in the configure1 function. So it starts from 0 and it is being advanced and then equated to counter max val, which if it equals this max value, it will trigger. This is where so now we see where the triggering of should save variable happens, and it is being triggered to set to true. The counter is being zeroed, so this counting will start again, and the counter max value is then being set to either 15 or 150. So this is interesting because this is the value that the counter is setting the should save value by. So if the counter maximum value is 15, and we know that the interrupt is triggered every 4 seconds, so it means that only every 15 times 4 seconds, which is 1 minute, every 1 minute this statement would be correct, and the should save variable will be set to true, and this will happen every minute if the maximum value is 15. Instead, if it is 150, it will happen every 10 minutes. And the should save variable again is very important, because we know that only if it is true will we save to flash. So as we already established before, every sample we are writing is one line like this. It is 13 bytes, and we now know that every line like this is being written once every minute or 10 minutes. So this is some piece of important knowledge. So now let's have a look at the second interrupt handler. It is this one. And again, this is the interrupt handler that handles the interrupt that was configured in the configured_to function. And like as we already established before, this interrupt is triggered by the accelerometer. So this is our interrupt handler, and we can see here that I'm not even going to look at the variables, but I'm just going to look at the logic here, and immediately we are testing whether or not this register pin D has a 1 value in the least significant beat. And if it does have a value of 1 in that beat, then the isTriggered variable is set to true. If it does not, then isTriggered is set to false. And then also the A variable is set accordingly, either to 2 if the pin D has a 1 value in the least significant beat, otherwise it is set to 3. Now what is pin D? So just again looking in the data sheet, trying to find pin D, we find this register name, and it says port D input pins address. So I'm not gonna do the whole research process again, but just going to the bottom line, pin D also correlates to the name of the leg through which we configured, of the pin rather, through which we configured the interrupt. So we remembered that we configured the interrupt in the legs 43, 44, 45. We see those names again here. So it is interrupt 0, 1, 2, and 3, but it is also called PD, which is pin D, 0, 1, 2, and 3. So what we are doing here essentially is testing whether or not this interrupt was caused by the accelerometer module. If it was triggered by the accelerometer, then we are writing a 2 in the A variable and then setting the isTriggered to true. Otherwise, it is being set to false and A is set to 3. Now, A is interesting because we are then using it to create the structure that we will then write to the flash. So format save takes that A variable. The A variable is what we are used to seeing as this 0, 1 value in all the other data structures. But if the structure was written by this logic here, then it will either be 2 or 3. And the value being sent here is the length. So this is interesting because if the A value is 2 or 3, the length will always be 0, and this buffer is never written to. So essentially we're just using this interrupt to write in the flash some sort of a break between data sets. So something might happen before this interrupt and we would write down a different set of structures, but then if the accelerometer triggers an interrupt in our system, this will cause a structure to be written which is basically just a 2 and no length, so just a few 0 bytes. And if we look again in the flash dump, we can see that we can quite easily find these structures, as expected, they would break a sequence of data structures that actually contain information and start with a 1, and then we have this structure being written here, which starts with a 2, and then 4 zeros because we have the length, which is 0, and then the 3 constant 0 bytes we have, and then the data would continue. So the last important part about the interrupt handler of the second interrupt is the is_triggered value, because again we see this value is only being either written or viewed only in the interrupt handlers. So what will happen here is let's go for example through a case that the accelerometer did trigger an interrupt. So this function will be called and this if statement is true, and then the is_triggered variable is set to true, besides of course the a being set to 2 and the structure of 2 and 4 zeros being written to the flash, but also the is_triggered value is set to true, which means in the next time the counter is equal to the maximum value, the maximum value will be set to 15. So a sample would be written every 1 minute, and this will happen until the is_triggered variable is set back to false. And if it is set to false, we are expecting a structure of 3 and 4 bytes being written to the flash, but also the is_triggered variable is set to false, and that's why this condition is not met, which means the max value will be set to 150 and a sample would be written every 10 minutes instead of every 1 minute. Now we understand what the code is doing. We understand the while one loop, the formatting, the writing to the flash, and the operation of both interrupt handlers. Now what is clear that's happening here is that we have these reset structures. I could only find 2 of those, and the start of the structure would have to begin with a 0, an 8, and then 3 zeros. And that gives us the absolute time value to start counting from. We know each structure that starts with a 1 gives us a time interval, because it means either 1 minute had passed or 10 minutes passed, depending of course on which value, either a 2 or a 3, was set in the beginning of the block. So this block, for example, of values all start with 1 obviously, and they hold latitude and longitude information, but the block itself starts with a 2 and 3 zeros structure. So I know now that if this is the beginning of the structure, each one of those structures is written in 1 minute intervals. And for example, if I look for a case of a different structure, that starts with a 3, for example, this one, then I know this block of values are separated by 10 minutes between each structure is written to the flash. So now being given an absolute time value by this structure type that starts with a 0, we can start counting and accumulating time periods until we get to the exact time that we are looking for. And again, this is stated here in the question. We are supposed to know the location at this exact time, which is 21 minutes past 1 a.m. on the 30th. So all that's left now is to look for an absolute time structures, which is, there is one here, but I know because I've searched before, I know there is a second one which we will start counting from. So this is another one. It contains information of absolute time, and we can interpret that as so. This is 17 minutes past 4 p.m. and the date is the 28th of October 2018. So this is our timestamp, our absolute time, and we can now start counting time intervals. Of course, I could have done it with some sort of automatic tool, either a Python script, but I figured it's not very time consuming to do it manually as well. So now that we have an initial timestamp, we need to calculate the number of minutes we need to count in order to get to the target timing. So the timing of the first timestamp is 17 minutes past 4 p.m. on the 28th of October. And our target time is this. It's the 30th of October, 1 a.m. and 21 minutes. So a simple calculation gives us a difference of 1,984 minutes. So this is the number of minutes in time intervals that we will need to sum up. Now, again, this is the initial timestamp, and this 2 and 4 zeros are the beginning of the block written by the interrupt handler. And from now on, every line is a structure which signifies 1 minute. So we simply need to accumulate time intervals until we reach a sum of 1,984 minutes. So I just copy-pasted the hex dump to a text file, so I will have an easier time commenting on it. So this is our familiar hex dump, and this is the reset block, the reset structure, and the second one is here. So this is the initial timestamp, and this is the beginning of the block. Now each line, again, is one structure and signifies 1 minute in this case, since the block starts with a 2. So I just summed it up, the number of lines in each block, and wrote it down. So until now we have 106 lines, which is 106 structures written of 1 minute each. Now the second block starts with a 3, so each structure signifies 10 minutes, and I just counted the number of structure in each block until I reached 1,984. So I reached this structure written here, and this structure written should have the latitude and longitude values at exactly 21 minutes past 1 a.m. on the 30th of October. So let's try it. And these seem to be the GPS coordinates that we were looking for. So good job for finding the bad guy.